Another midterm?
Yeah.
Hold on 1 second. Hold on 1 second. Okay. So, did you have a good weekend?
Yeah.
Yes. Who said yes? I love it. Why? What happened?
I study.
You're done with the exam?
No, I haven't got any yet. But no, I just
You feeling good?
they're fun, you know.
Exams are fun?
No, it's weekends in general.
Oh, weekends in general. Okay.
It's always fun.
All right. That's one way of looking at it. Good. I like that. What else? Who said no? Were you studying for this exam? Hopefully, yes.
I get today.
I was waiting for someone to say, oh, the study for this exam was fun. Anyone? Anyone? No? Okay. Well, I tried. Okay. So, hopefully you've studied, yes. Because if you didn't study, it's gonna be tough, okay? But if you did study, it's not a difficult exam, okay? So you should be able to go through it pretty straightforward, you know, the things that we did in class. You have the review questions, right? And the solutions as of yesterday or Saturday, whatever that was. So you try those, and if something doesn't work, let me know. You got the announcement, right? So tomorrow we have an office hour out of you know the norm because it's the day before the exam. So I'll be on Zoom. You have the link. Hop on if you have questions. I'll try to answer them. Again, if you have questions today, tomorrow, let me know. Not 9 p.m. on Tuesday, okay? I probably won't be able to see it, okay? So that's one thing. A couple of you asked questions about how the exam is obviously in person. You should know that by now. Same place, okay? Same time, don't be late. You're not supposed to bring any notes or formula or cheat sheet or anything. I'll give you all you need. All you need, apart from that, is a calculator. Okay, calculator, you should all have it. Your iPhones have calculators, you know, engineering calculator that is, okay? You need to do some angles and, you know, whatever, square roots and so on, okay? So, what else? Do you have questions? What's your question?
Yes, for homework, you assigned some homework that was labeled statics. Were we supposed to do them because they weren't covered?
Statics.
5.1, 5.1.2, and just on the Pearson.
Yeah. On the Pearson, whatever you have is part of the line. Yeah. You had a question?
Oh yeah, so you mentioned that you're going to give us a formula sheet, or what was that?
On the day.
Okay. Is it possible if you could like, so we can see it, so we can...
I mean, it's got, okay, I'll go through the equation. It's going to be sigma equals E times epsilon. You know that, right? What is sigma? What kind of stress? Sigma versus tau, what's the difference? What's that? Sigma is normal, shear is tau, yes, right? And then sigma equals E times epsilon, E being Young's modulus, plastic modulus, epsilon being strain. What kind of strain? Normal strain, right? And then we have the same exact, pretty much, equation for shear stress and shear strain, which is what? Tau equals G times
gamma?
G times gamma, yes. I mean, hopefully you know these by heart by now. So, these are the equations that I will give you. Okay, so you don't need to memorize them, but hopefully we've done enough of these that you know what's what, right? I think one thing is you need to know all these Greek alphabet, right? So don't get confused by those. I'll give you what sigma is, for example. I'll write it in the exam sheet, exam notes, okay? But imagine you being in the middle of the exam stress that as it is, and then you have to go back and forth looking what was what. Okay, so please do a little bit of graph for that. What else do we have? We have the equation for T, right? Or yes, TV, the torsion, right? What was it again? Oh, let me write the other one first. So it's going to be NL delta equals NL over AE. Right, this was the equation for what?
Deformation, axial deformation.
Axial deformation, right? Elongation or compression. And then N is what? Force. N is internal force. L,
The length.
Length.
The
A,
area cross section.
and E,
Young's modulus.
that's one. Okay? And this is, you know, I mean, I can tell you definitely you will see something like this, right? You have a member, you have different loading conditions on different parts of it, and then you need to use, what was that called? Method of sections. Very good. So you find sections that have a constant A, constant E, constant L, and then you solve for that section. What is L in that case? Length of that section, right? Not length of the beam or whatever. So then you have different sections, and then like you sum them up, right? Okay, good. And then we have another one for angle of twist. For torsion, remember that one?
TC over GJ.
TL over GG.
Yes, good. TL over, yeah. J being polar moment of inertia. G is shear modulus. T, original moment, right? And then L is the same. What else? Well, there's one more equation, and that is the Poisson's ratio. Poisson's ratio was what? So this guy right here is gamma.
Negative.
Okay, this guy right here is nu. Okay, don't mix them up. Nu is Poisson's ratio. Poisson's ratio, which is what?
Negative. Lateral strain.
Lateral strain over longitudinal strain, right?
One question.
Yes,
What's the Greek letter of it's mu, right?
mu. We didn't have mu in this class, but mu is like G. A lot of textbooks use mu as shear modulus, but we didn't have mu here. Okay, so again, Poisson's ratio, I will give you the equation, which is minus E lateral, epsilon lateral over epsilon longitudinal, but you should know that Poisson ratio, is it a positive value or negative value? Okay, that wasn't confident enough. One more time. New Poisson ratio, is it positive or negative?
Positive.
Positive. Do you need to memorize that? Can you tell me if it's positive or negative based on this equation?
Yeah.
So, simplest example I can give you is there's a member, right? And I stretch it. What is the longitudinal strain?
Positive.
Is it positive? Everybody agree, right? I'm stretching it, right? This is getting elongated. So the denominator is positive. What about the lateral strain?
Negative. Because it's decreasing.
Right? That shrinks. So you pull it on one end, it shrinks on the side. So lateral strain is
Negative.
negative. And then you have that minus sign there.
So it
Poisson is always positive. Poisson ratio is always positive. Okay? And in fact, we talked about this, right? It's less than 0.5 always, between 0 and bless you. Okay. I actually think that pretty much all the equations that you have. What else am I missing?
J, that's J.
Oh, I'll give you the J's. Yeah. So now that you talk about it, so let's say this is a shaft that is solid. J there was, who remembers? Somebody remember last time? Okay, looks like everybody knows this, right? C being what? C is the radius. Okay, and then what if this was a hollow cylinder? Or a tube?
Outer radius less than
C out to the 4, C inner to the 4, right? You know, as outer and inner, right? I think that's just it.
What of the compatibility equations? They're
What's the compatibility equation?
equation from constraints, like we use the equation to apply.
Can you say that louder?
The compatibility equation is an equation derived from the constraints of the model that is used with the equations we find in the notes.
Right. So what is that equation? So that's the case where you have more unknowns than you can determine, right? That's an indeterminate problem. And the equations there where, so for example, you know, in the case of say a column or a beam that's fixed on both ends, right? What's the equation there?
The sum of the deltas equals 0.
Yeah, some of the, what's you know, more simply said, this distance is fixed, right? So the whatever change in length you have is going to be inside. This distance is fixed, right? I don't think that's something that I would need to give you. Hopefully you know that, right? Anything else?
How about like when you have like your compressive force and there's two beams and then they shrink a little bit and there's the beam in the middle that now hits like a little bit of this piece.
Wait, so what is this again?
So like, yeah, I'm curious, I want to remember the formula set, but like you have like, let's say you have like two steel beams, like, and then like a smaller one in the center that's just not small, and then it infinitely push a plane, and then it squishes the beams that are equal on the left and right, and then the middle one after a little bit.
Yes, I'm not sure I totally understood which problem that is, but the same thing, right? If the two ends are fixed, you know the length.
Yeah.
If they're not, then you know how much kind of tolerance there is, right? That's another example that you should probably know how to solve, right? You remember you're applying some tensile load on a member, right? And there was a little bit, like 0.2 millimeters, I think that was the example. Of extra room. So you need to fill that and then calculate the amount of extra force or resistance, basically, right? Same deal. So you know the geometric constraints there, and you apply them. Yes? The what? What's a blue book?
We don't need it.
What is it?
I think you have to buy for it. It's like it's just like a test book.
No.
It's like a test packet. Some professors require it.
No. I'll give you the physical exam books and you write in those. Sound good? Okay. I don't know. We'll see. It's gonna be, how many minutes do we have in the class?
120? No, sorry.
No. Somebody's not having fun in this class. Yeah. So the way I do the exam is I design the exam and I take it myself, right? So I try to write everything and then I give you between 2 to 3 times that much time, okay? So it will be fair in terms of the time, okay? Don't worry about how many problems there is, okay? Oh, one more thing, I've said this before. So in the Pearson thing online, you get points when you have the right answer, okay? But in the exam, you get points for the process, okay? So when you write. Of course, don't just write things on the paper, okay? You won't just get points. But, you know, if you write it out and you use these equations and then you have a, I don't know, calculation mistake, you'll get partial credit there, okay? So, do that.
Well, today's material was good.
No,
So
No.
it's just gonna be 1 through 5.
but yes, until the end of 5, which is torsion. Today is not in the exam. Yeah. So, I mean, I guess that's fair, right? So I wanted you to go through everything, do the homework, see where you made mistakes, you have time to ask questions and so on, and then take the exam.
Are you gonna focus more on one chapter, or is it pretty?
I don't think you need the answer to these questions. You're just
Yes.
stressing too much over. It's going to be of all the 5 chapters, right? Probably less on the introduction of chapter 1, you know, obviously. But you already know what the questions will be, hopefully. You know, you'll get one with the method of sections for axial load, one for torsional load, you know, something like that. Okay. Yes.
So in one of the later chapters, I think it's like section 4.7, it's talking about like how like heat transfers and like a part or whatever. Are we gonna have something like that? Maybe. Because we haven't really gone over it in lecture.
4.7, you say?
I think. I don't know. It's been a while.
4.7. What's 4.7? Let's see. Oh, stress concentration. Is that what you were asking?
Yeah, I guess.
No, I won't give you anything on stress concentration. Hopefully you've read it. That's an important kind of engineering concept. But yeah, you're not likely seeing anything from there. Okay. All right. So one more quick thing. So you got this, right? Everybody solved this? Good. And you got the final answers, I guess. I think this is from the book, but you know, one thing that I wanted to mention. Wait. We drew up this torque versus X diagram. Or in the case of axial load, we drew up the force, internal force versus X diagram, right? Do that for the exam, okay? So again, you start from, say, the right end of this, right? X equals 6.5 at point A, and then you make your way to the left, right? You draw that diagram there, because that helps you, right? Because from here, you will be able to see that the torque is constant at minus 10 kilonewton meters from x equals 6.5 all the way to x equals 5, right? that's your section, basically, right? This goes hand in hand with your other section. This should help you a lot, right? Again, you can do this for the axial load as well. And then every time you have a point force or an external load that's added to the problem, you should expect a jump, right? So for example, if this is point A, remember that, yeah, it doesn't matter. I mean, I think this one went from one end to the other. Yeah. So we have 10 kilonewtons at D, right? I think I said A by mistake, but this is D. So at D it has 10 kilonewtons, right? Oh, you don't see the mouse. So here there is an external torque of 10 kilonewtons. This is negative or positive. There was a few questions about negative or positive. This is important, right? It's not important to assume one direction is negative and the other is positive, but it is important to stay consistent, okay? The convention that we use in the class is what? Is that 10 kilonewtons? Is that positive or negative?
Negative.
Negative. Why?
This points towards the,
Right. So if your forefingers are the direction of rotation, right, or the torque, your thumb is the direction of that vector. And if it's pointing inwards, that is taken as a negative sign, okay? So that D has a negative 10. It starts with a negative 10 up there, and then it's constant all the way to point C, where we have an additional 60 kilonewtons, still negative, right? Because that's also in that direction, right? So you had a 10, you had a negative 10, you add another negative 60, it becomes negative 70, right? So negative 10, negative 70, and it goes all the way to point B, at which point we are applying a positive, right? This is the other direction, a positive 150 kilonewtons.
Why is the 150 positive if the rule still applies? So when you curl it, you're still pointing inwards into the rod.
That's not inwards, right?
But the third is going into the rod though. It's going out. How's it going out?
Okay, so where are you making that cut? Is it before B, right? If you're going from that side, you make the cut before B. But then when you get to B, that's the positive value, right? So in the AB section, that is positive value. Okay? Right? I'll make it simple. This has a different direction than those. So if those are negative, this has to be positive, right? That's the consistency there. But the reason behind it is this. So when you make a cut and you're looking at AB section, that is the direction. So in the AB section is pointing out. And that's where the jump goes to positive 150, which, we had a negative 70, we go up 150, so that's positive 180. Okay? So this diagram will guide you through everything. So you have this, you know the length, you know the assigned Young's moduli, in this problem it's a constant value, so that's easy. But if you need, you can use that. But this tells you the lengths. It tells you, right, with each section what area you need to calculate and so on. The rest of it is just plugging everything in that formula, right? This diagram helps you a lot. The same for axial load, where your y-axis will be N, that's in newtons. Your x-axis remains the same in meters, okay? All right. Sound good? Any questions? All right, so what I will do is I want to continue with our materials so we don't fall behind. But if we get to kind of finish this early, then I'll let you go. If you want to stick around and ask questions, you're welcome to. If not, you can go and read more on your whatever for the midterm exam. Okay? Good deal? All right, so we are starting with bending now. So can someone tell me the two types of stress or strain, for that matter, that we studied so far? What were they? And we repeated that today too. We had normal and shear, right? Normal is easy. You're applying, you're stretching, or you're contracting. Either way, you have the stresses, the deformation all perpendicular to that cross section that you're interested in. Correct? Hopefully everybody sees that easily. Then we talked about shear strain and shear, stress, and we had that in two different ways, right? One was if you're applying a perpendicular load, right? If you're applying a shear force to, say, a beam, right? What happens at that cross section? No. You're applying force. You're applying force, right? So assume this is the beam. You're applying some force here. So what happens is under there is that. Very good, very good. So you see shearing force. It is tangent to that plane, right? It's inside that cross section plane in terms of loading, stress, strain, and all of that, right? So these are the main two things that you deal with. And then we kind of got familiar with the concept of a moment, which is different than a force, right? Moment is different than a force, but the effect of it in terms of the amount of shear, the amount of strain that you see in the material, the effect of it could be similar, right? So what was the effect of a torsional moment? So torsional moment, you're twisting that member, twisting that shaft, whatever you have. So what happens there? So let's say I look at this cross section again, same place. What's going on there? Are you going out of plane or in plane? Oh, okay, right. So the big, okay, right. So you have twisting, right? In that plane, you have twisting. So is this more like a shear or normal stress? Shear, right? That's literally the whole torsion section of the book, right? That we covered. So that's more like shear, because if you think about it, at that cross section, what's happening is, these cross sections, these planes, if you will, they're kind of getting sheared, and there's going to be some angle, right? Angle could be a good indicator of shear, right? So if you had all these longitudinal grid lines, if you twist it, those grid lines will have an angle, right? That indicates shear strain. Shear strain, we use gamma to show shear strain, and gamma and shear stress are related through shear modulus, right? Now, the other type of moment that is not torsion is bending moment, right? And I'll show you in a second why these are different. But bending means what? So let's say you have the same beam, right? And bending is what? So shear was this was torsion, right? Bending is, so when you hear the word bending, what happens? So this is the beam, it becomes bent, correct? In terms of the vectors in the 3D world, how are these different? So, this is torsion, right? It is so tough to draw this in 2D. Yeah, this 3D problem to draw it in 2D. Let me So this is, so I want to show that with a vector, for twisting moment or for torsion moment, what is the vector? Is it in the direction of the long axis of the shaft or perpendicular to it? I see people nodding, right? That's perpendicular. Why is that? Because the direction of rotation, if it's your forefingers, right? That's what's happening, right? So if you want to make a twist, if you want to twist that shaft, the arrow representation of that, the arrow is perpendicular to that cross section, right?
Wait,
Yeah.
if it's rotating this way, should it be pointing towards the bar, not?
Yes. You're right. And you have another one on the other end, right? Now, what is the difference between this and a bending moment?
It's essentially like it's coming out of paper and all of it.
Right. Does that make sense? So for bending, remember we said it has to bend this way, right? So you're applying force that way to the two ends, let's say. And so I will show you a side view. What's the arrow?
Coming towards you, like.
Right? So that's the difference. Remember, the normal force is perpendicular to that plane. Shear force is tangent to that plane. Same deal applies here, right? So if your angle of twist is in that plane, that is torsion, but if the angle of twist is coming out of the board perpendicular to it, that is bending, right? So the bending moment would be something like this. And the arrow is coming out of the screen. Does that make sense? Right? So I don't have a bigger. Aren't these supposed to be? So, what's the torsion? Twisting is that way, right? What's bending? It's that way. You see how they're different, right? I mean, this was my best attempt at 3D visualization here. One more time. So twisting is, you kind of, twisting. You call it twisting even, right? I think that makes sense. This is the torsion, right? So you see the letters on here are moving with respect to each other, right? If you think of all those longitudinal lines, but then bending is that way, right? So it applies the force in a perpendicular to what we had as torsion. You had a question?
Yes, you symbolized the direction as a dot and an arrow.
Well, no, I mean, I don't think that's official. Wait, but so I think the way you showed with a dot and a circle that's coming out, and a circle with the circle dot going in. Yeah. But I just wanted to, I think that marker example was best. So what's a good example of bending moment? Wait, tell me again, what was the good example for torsion? Mechanical engineers? What's a good example for torsion?
Shaft.
Shaft is a good example, right? Power transmission with a shaft, okay? And then for bending? A bridge, yes. Maybe more civil engineers, but still the same. So bending of a bridge, I mean the loading of a bridge, how is that bending again?
Because there's a car coming on it, there's weight on it.
The weight of the bridge itself, plus the weight of the cars, whatever that's ongoing there, that's causing the force kind of in the middle. Or if you think about it, so if I have a vertical load on a beam, is that bending again, or torsion? Do you think? So if you look at it, so you have a beam, you're applying load here, what's your reaction at the ends, the moments? Those reactions are bending moments, correct? Of course, it's not that simple, and lots of things happen on a bridge, but you can think of it that way. Yeah, so these are a few examples that I found in the book, which is interesting. So simply supported beam, I think that's the easiest example. We just talked about that. Cantilever beam, right? That's the same, right? So assume that this has a lot of weight itself, right? It's a very high density material, or you have some load, distributed over it. That causes this to bend, obviously, right? And then overhanging beam, kind of a combination of these, right? So, if you want to design a beam, and make sure it doesn't fail, right? You want to make sure your bridge doesn't fail. What do you need to consider here?
Maximum load stress before yield support for the braces.
Right. So you need to pay attention to the maximum amount of shear load, which was V. Remember that diagram, right? You probably remember this from statics, and the moment M. And just like I showed you in the other slide, where you have your y-axis as the torque, say with that particular example, that was torque, and then you have your x-axis, and you study the changes in this torque along the x-axis. We do the same here, right? You see how much the m, being the moment, varies as you go along the beam, and how much v, being the shear force, varies along the beam. And then you make sure that you are always below that certain threshold that you have, so it doesn't fail, okay? Right. Okay, so that was kind of the intro. Obviously, we want to understand what internal moments and shears at any section of the beam are. So, this is a quick example, right? Just focus on that top row where we have the beam. We are applying on the left an 80 kilonewton meter moment. Again, is this moment bending or torsion? It's bending, right? I mean, literally, if you apply that, it will bend the beam. You should see that. And then we have a 15 kilonewton point force at point B. And then what's happening after point B? We have distributed load that's applied vertically, and that's a constant distributed load, right? What's a good example of that? Like, what is the difference between that 15 kilonewton point force at B and then the distributed load between B and C at 5 kilonewton per meter? I know you all know this, but let's do it quick. What's the difference there? Can you think of a good, like, real-world example? What is that 15 kilonewtons? Anyone? This should be simple, right? You're just applying some load at that point B. I mean, that could be a column right there, or you can have extra weight at that single point, or yeah.
Is it the weight of the beam?
Well, is it the weight of the beam? Anyone? It's not the weight of the beam? Why not? Why not?
The weight of the beam would be distributed across the whole beam, and that's only 15 kilonewtons on one point.
Right.
Oh,
The weight is usually distributed, right? If it is a small scale in terms of the size, right? If it's small scale with respect to the beam itself, you can assume that as a point, right? So let's say you have a column that's this big, right? In the middle of that beam, but the beam is like, I don't know, 20 meters long, right? So you neglect that size and you say, okay, there's only one point that's applied. But if you're thinking about the weight of the beam itself, it is distributed, right? Or if you have extra load between B and C, I don't know, people are standing there. This is a location where people stand, for example, right? That's a distributed load. But of course, you know, we can kind of go between these, right? So how do we find the reactions, remember, for free body diagram, for distributed load?
Central.
Right. We find the equivalent force, equivalent point force of that distributed load and apply it to the centroid of that. Okay? So, I mean, here you have all the information, but let me give you an example here. Right, I'll go back to that previous slide in a second. But let's say you have supports at A and C, you're applying load P at the end point D, and then you have some distributed load, and that distributed load is not constant, right? So this looks like a complicated problem, okay? So how do we go about solving something like this? First thing is what? I mean, always. Free body diagram, very good. So, free body diagram here, any idea how we do the free body diagram?
You should start by drawing a beam.
Okay, that's good. What else?
Draw the applied force P.
The reaction force of the joint is
We have two reactions at A and C. What else do we have?
A normal reaction at C.
Usually we have the reaction forces and moments, right? We have the moments also, and then you write, there are three equations. Whatever you want to do in statics, there are three equations. Sum of forces in X, 0, sum of forces in Y, 0, sum of moments around certain point, 0, right? So you do that, and then you get to all these, forces. You have the reaction force at A, let's say in this example, you have the reaction force at C. You know the moment, 80 kilonewton at A, okay? So this is what you're left with. And then you start from point A. So what's the first section? Let's say you want to do your shear force, V. Okay? Shear force V. Can someone help me kind of draw this diagram or understand the diagram? I've already given you what it should look like. So start from point A. Let's say we know this arrow at point A, which is 5.75 kilonewton. We start from there, and then from A to B, that's pretty much all there is in terms of shear forces, right? That's all we have there. So we end up with a constant value there at 575. And then what happens at point B?
So applied concentrated load of 15 kilonewtons is applied.
So you basically go down by 15. So that should be giving you what?
Negative
975?
9.25.
No. So 575, right? 575, you go down 15. What happens there?
It goes negative.
Yes, negative. But does this number make sense?
Yeah, because 5.75 plus 925 is 15, so 5.75 minus 15 should be
975.
975.
I don't know, my math is not great, but I think it should be 975, right? But then you have something else there too, right? You have to consider, what else is there?
Distributed load.
There you go, right? So you have to count that in as well. So then you get to 925, right? So, okay, we'll do an example. You don't need to solve this all right now, but I want to kind of go through the process of what we do. So let's say we get to 925, negative 925, and then what happens here? Why is that at a slope as opposed to that guy right there, which is constant value?
Because the load applied increases with every meter on the bar. Like
Yeah, so depending on how far you are from point B, essentially, that load is increasing, correct? Everybody see that, right? That's the definition of a distributed load, right? The distribution is the same. That's a uniform distribution of load. But then as you go from point B towards right, towards point C, you see more and more of this load. And that's why you have this slope here. I think that's essentially the difference between a distributed load and a point force, right? A point load. That's the difference, right? Point load, you see a jump, right? In the point load, you see a jump, and then it stays constant, whatever that is. But in terms of the distributed load, you have a slope. Okay? And then what do you expect this number to be at the end? What do you expect that number to be at the end? 34.25 has to be exactly like negative though, right? So when you have that external reaction force, it goes down to 0. Right? That's the deal there. So if that number doesn't look like that, you've done something wrong. Okay? And then we'll derive the, yes?
I have a question. So, in the center, I guess I'm a little bit confused with what you did in the center. So why did you add 5.75 to 15 to get negative 0.25? But why isn't there just like, because on the ends there's like, so the points are just equal to the forces at the end in the graph. So why in the center is it not like that?
In the end, say that one more time. In the end, they're the same as?
So in the graph, the points, the y-axis, V kilonewtons, is equal to the force at each end of the beam. Whereas in the center, it's like you added.
That's a good question.
Side. Like, why does it do that?
So who can tell me, who can help me answer this question? So the question is, well, we start with 5.75, which is the same as reaction at A, and then we end at 34.25, which is the same as reaction at point C. So, bless you. So that's the forces, and you see the same exact thing on that diagram of V. What happens in the middle? So why don't we have 15, right? Or something. Is that the question?
Yeah, pretty much.
So why? Who can help me?
Like if you imagine, like you put your finger across the beam, so you start, you have a positive, or in this case positive, as we noted, 5.75, and you move along it. It's always going to be 5.75 until you get to the point of 15, in which it's now 15 minus the 5.75 instead of opposite direction, which is how you get negative 9.25. And then you follow the forces again, but you see that the 15 kilonewtons goes down to 5 kilonewtons per meter. So that's at the end eventually going to get to negative 34.25. So because it's this diagram.
Yeah. Does that make sense? Well, okay, so does this look like the method of sections that we've been doing? That was a trick question. The answer is yes. It is the method of sections. If you think about it, you start from that end, and then whenever you have an additional external force, there's going to be a change in your V diagram. Okay? Essentially, this is your internal shear force diagram. Right? And that's what you do. So you start from that end. The reason why that number is not equal 15 is you already have some internal force in the beam, and then you apply that 15 on top of it, right?
So that total negative 34.25 is essentially because like the force in C now has to totally cancel that out.
Right. So you have to consider equilibrium always, right? At every point, you need to have equilibrium. So that's why when you make a cut, right, so you have 575 internal shear force, and then you make a cut there, that has to be equal and opposite in direction. Yeah, that's the reason, basically. Okay? Good one. So hopefully, I mean, we're repeating this over and over. You all are familiar with the concept of equilibrium, but you need to kind of see that everywhere, right? In these static problems, you need to have that always applied. Okay? Again, a couple of notes here. Does it matter if I start from left or right? Right? It doesn't matter. It's arbitrary, right? So you can start from point C and say, okay, so that, at point C, I need to start from 34, 25, and then go to the right. Usually the convention is you start from the left and move this way, okay? So, that your axis of, basically x-axis is arbitrary, but you know that already. And then the other thing is, you see these, what we call discontinuities, right? So the number is 575, and then all of a sudden, it jumps to negative 925. You've seen this before, right? In the case of moments, or torsion moments, or axial loads, right? You're already familiar with this, but this happens when? Every time that we have an external force or external moment or something like that, you will see a jump there in the shear force, especially. Okay. So let me make that more clear. So whenever you have an external shear force, right, you see a jump in shear force diagram. Whenever you have an external moment, you will see a jump in the moment diagram, right? So this is a continuous graph. There's no discontinuities here, because why? Because we don't have any moments applied externally in the middle of the beam. But if say we had something here, you would see a jump at this point to some value. The same way you see now in the shear force diagram. Okay. So the reason why I say this is similar to method of sections is that these shear force V and moment, internal moment M, you deal with them wherever they're kind of between these two discontinuities, right? So so here in this example, we start from A, we go all the way to B. So we have AB as one section, and then we have BC as one section, as you would imagine, right? That there's no force there, so it kind of stays constant there. So you take that as an extra. And then you have the external force C applied here. So this is another section that you need to look at. So likely you will have, I mean, definitely you will have a jump in shear force at point C. And then you go all the way to D. Right? So like before, you look at AB, BC, and then CD, and then calculate the shear forces inside for each of those regions. Okay? One more thing about the sign convention, as always. Can you tell me what the sign convention here is? I have 3 diagrams there. Positive external distributed load is that top row. Then positive internal shear is that middle one. And positive internal moment is that bottom one. So let's look at the shear. Does it make sense that that is positive? Distributed load we call positive when we have upward arrows. That one's easy. But for shear, it's a little more complicated, right? You can see both V's here are considered positive, but one is pointing up, one is pointing down. So what's the deal here? Yeah.
One question. These are at the cuts, right? When you cut.
Yes. I mean, V and M here are internal forces and moments.
Could you say that, like, this is just kind of a shot in the dark here, but if you kind of did the right hand rule with the 2 V's, that, like, it would point outwardly towards you? Because, like, if you follow the right side V arrow, and you kind of go, your thumb kind of curves out at you, and maybe you could point it inwards, it would be negative, but if it points outwards, it would be positive. I'm not sure.
Yeah, good. There was someone else? Does that make sense, everyone? So, okay, let me ask you this first. Does it make sense? Let's say this is positive. Let's assume we agree that that one on the left is positive. Does it make sense that this is also negative, positive?
Yeah.
Why?
It's shear opposite sides.
It has to be, because it's the same, I mean, in reality, it's the same location, right, inside the beam. You just made an arbitrary cut there. Right? That's the section that you decided to look at, correct? So whatever happens on the left is true for the right as well, right? We had this before. Where did we see this before? I mean, it is true whenever you make a section, right? Remember for that twisting moment? Last session, I mean, I showed you the example today. So one thing that kind of was confusing to people was that you have a moment that is, rotating the left end of the beam that way, so counterclockwise, right? What happens to the moment on the right? Because these two are opposite, the same value but opposite directions, right? But I think we all agreed that those are both positive. Because if one is positive, the other has to be positive. Doesn't matter what direction. Yeah? Does that make sense? So how does that work here? So the convention is, if your V is, if the shear force is causing a clockwise rotation, that we take to be positive. Okay? So is that a clockwise rotation?
Yeah, and does that mean that if the moment causes a the moment.
Hold on to the moment for a second. Let's agree on V for a second. So do you all see that V is what was I gonna say? Clockwise rotation here? Yeah, we take that to be positive. So on the left, it's clockwise, kind of rotating the whole thing, clockwise. On the right, it's still clockwise, right? Even though the arrow is pointing in different directions. Okay? So that's for V. And then for M, question.
So it's clockwise in, like,
Right, so because of that V, the beam will rotate that way.
Right, okay, and then, yeah, okay, so this is clockwise in relation to the beam, got it.
Yeah.
Okay, got it.
And for M, what do you see that's the same in these two M's?
I was going to say that they were counterclockwise, but then I saw that the other one realized that it was going clockwise as well, so.
But what happens to the beam after this M, if you think about it? Do you agree that it will be something like this? It's like I'm pulling on the bottom surface of it and then pushing on the top surface, yeah?
It compresses on the top and tension while it elongates at the bottom.
Yeah. Is that true for the right segment?
Yeah.
Same deal, right? So it's like this moment is compressing the top surface and then extending the bottom surface, right? And that's what we take to be positive. So if the dotted line is what it used to be, now it's going to be something like that. Okay? Hopefully that's not too confusing. But again, the sign convention is just a convention, right? The most important point here is to be consistent, right? So if you take this to be positive, you always need to take this to be positive, right? You can't switch in the middle of solving the problem. That will kind of screw everything up. But if you take this positive and continue, you should get to the right answer. If you take this to be negative and continue with that convention, it still works, right? But for the purposes of this class, we take these to be positive directions for shear force and bending moment. Right? For torsion, it was a little easier because torsion, the arrow is kind of, either clockwise or counterclockwise into the screen, into the paper that you have. It's easier to imagine. For this one, like I said, the arrow is pointing out, so it's more difficult to, definitively talk about it that way. So the convention is whether we compress the top fibers of the beam or not. So, let's do a simple one. Draw the shear and moment diagrams for the beam and determine the shear and moment throughout the beam as functions of x being between 0 and 6 and between 6 and 10. So what do you think we have here? Where do we start again? Free body diagram, right? So what's the free body diagram here? Can you help me?
So you have a reaction portion.
You have two support reactions at where the beam is connected to the surface.
Yeah, what else? Is that all?
You have several moment force at the and two concentrated loads and
No, wait. So here, at this end, what do we have?
Two support
What kind of beam is this?
reactions.
Okay, so what do we have on the left?
Two support reactions.
And a moment, right? So I have two support reactions, f of x and y, right? And a moment. Don't forget the moment. What's the x force? That one's easy, right? I don't have any other x force here, so. What is the y force?
The sum of all the applied and distributed loads.
Okay, so what is it?
30 kips.
Let's see, 30? 30. Everybody agree? So how did you calculate that? You have an 8 here, and a 10, so 18 negative.
And 2 kips per feet over 6 feet is 12 kips.
So 6, right, 6 feet times 2, that's 12. 12 plus 18, that's
30.
negative 30, right? So what you need there to have is a positive 30. Good. That's good, right? Everybody agree with that? So we have a 30 kip reaction force in the positive direction. So that's good. And then, what else do we have? I would say there's a moment there, right? So what's the moment? Okay. So we have a 40 that's trying to rotate this.
Oh, no, and then you have to also account for the other forces and the CT.
This is positive or negative again?
216 kip by feet moments.
It's a negative, right? Because you will have tension up there and compression at the bottom. So this is, according to our convention, this is negative. Okay, so it's 40 kip feet, that's the moment. What else do we have there? That A kip is trying to also apply rotation there. So what's the moment, the corresponding moment to that? A times 24?
Oh, wait, no, sorry.
Why 24?
Sorry, I almost wanted to say something. I meant to add.
So 8 times 10, that's 80 plus 40 or minus 40? Are they same direction? Same direction, they're both, right? So 80 plus 40, we have 124 so far. Then we have the 10 kip,
10 to 6.
10 times 6, right? Is that the same sign?
Yeah.
Same sign, all of them are kind of rotating this way. So 60 plus, what was that, 120? 80 plus 40 plus 60. So 180 so far. And then, that last part?
Like you define the, after you found the concentrated force from the distributed load, you find the
70, right? So this is 80, this one was 60. And then, we have the last one.
You have to find the centroid of the distributed load.
We have to find the centroid of the distributed load. So what is the centroid here?
3 feet.
So this is a uniform distribution, right? So it's the centroid of this is right in the middle. So 3 feet, okay?
And you know it's 12, concentrating 12 kips, so 12 kip by distance of 3 feet is 36.
So I want to replace that by that distributed load by a point load, which is of 12 kip value, right? And it is applied at the centroid, which is 3 feet away. Okay? So what's the corresponding moment here?
36 feet.
36, yeah? Everybody follow me? Good. Okay, so what is the reaction moment at point, whatever that's called, A, at the far left?
16 kip by feet.
So 80 plus 40 plus 60 plus 36, right? What did you say that was?
216.
216 kip
5 feet.
foot. Okay? So far so good? So then, is this the right one? That doesn't look right. Okay, I think I copied the wrong thing here. Anyway, so are we able to draw our diagram here for shear force and bending moment? Can we do it? Let's do. Last coming out here. So let's say this is v as a function of x. So where do we start?
30.
So we have 30. Is that positive or negative?
Positive.
Okay. And then what happens next?
It decreases linearly. Decreases linearly from 30 to 80 kip. You distributed load of 2 kips per feet.
Right. So, but you said that it's negative, right?
Yes.
So we start at 30. So what is 30? 2 so 12. It's gonna go down to what?
18.
I apologize for this small kind of font here, but so this is 30. It goes down to 80 because of the. Ooh, that's not right. So like this, right? So it goes all the way to this point, at which what happens? It takes a drop of 10 kip. So now we are. So it goes down to 8. I think the book has done a better job in drawing this for you, so take a look at that. But hopefully it makes sense, right? So we start with 30, which we found to be the reaction force here. That's positive. We start there and then linearly deduct from that 30 at a rate of 2 kip per foot, right? So after 6 feet, it's going to be 12 minus 12, so we end up at 18 right here, okay? And then what happens here is that we have a negative 10 applied externally, so there will be, you should expect a what? A discontinuity there. So it drops down by that same amount, 10, okay? And then
It stays flat.
stays flat, right? At 8. What did I do? So this should be your shear force. Okay. And then for a moment, what happens? We'll see that the moment is, you know, kind of, this acts as the slope of that moment graph. I'll derive the equation next time and show you how that goes. And then usually what you see in the moment diagrams, you see kind of curved lines, right? Because if you take an integral of this, you know, you see quadratic function, integral of that would be, you know, as if this is the slope of the moment diagram. So there the slope is a constant value, you take the integral, you get a quadratic function. Here the slope is constant. So then you'll end up with a linear line moment. But we can do the moment next time, I guess. But does this make sense? So at least for the shear force, you know, again, you know, I want you to, you know, practice this method of sections a lot, because that you see that you start from one end and then you go one by one. If you have the right two-by diagram, the rest of it should be simple, right? You just go from one point to the other and then draw the corresponding. I wanted to let you go earlier, but we didn't get that. But we have a few minutes. If you have questions, I'll be here to answer.